Ever felt like throwing your breadboard out of a window? Oh, thanks, ChatGPT. So that is what you think of me when I lose it in the lab. Okay. Today's video is about exactly that moment when you are deep into a project and you are completely stuck. Everything was working fine yesterday. Sure, you made some changes, but nothing big. Just moving forward with the project. And now, it's dead. No output, no response, not even a blinking LED. So, you start retracing your step. Check the wiring. Again. Those DuPont jumper wires. Maybe a pin has gone. Maybe a bug in the library. It could be HAL. Come on, be honest. HAL never behaves properly. That is what you are talking about today. The point where you ask yourself, do I throw everything out of a window? Or do I take a breath, again, and start everything from scratch? This happens to me. Honestly, every project. And judging by the comments and emails I get, I know I'm not alone, right? So today I want to show you how I use STM32CubeIDE to build myself a way out. Not just to set up a project, to write code and debug it, but to set a sort of breadcrumb trail. So if things go wrong, and they will, I can find my way back. Because yes, maybe I fried a pin, or I wrote over the end of an array. Maybe I pushed that midnight update, and I shouldn't have. Whatever it is, this episode is about breadcrumbs. In this video, we are not going to explore new devices like a new LCD display, a memory chip or a fancy sensor. And we won't dive into STM32 built-in features, timers, communication ports and so on. Instead, we will focus on the STM32 IDE and how to use it to effectively manage our project, with a specific focus on what we need to prepare to be ready for testing and debugging phases. Like always, we are talking about hobbyist-level projects. This content is for those who develop projects individually, for passion, for study and self-growth, or experimentation with new ideas and techniques. Okay, let's open CubeIDE. In its default configuration, unless you have changed the settings, first thing CubeIDE asks is which workspace you want to access, giving you the option even to create a new one. A workspace is essentially a folder that can contain multiple projects, and each CubeIDE project is a workspace subfolder containing all the information needed to build, test, and debug a program for an STM32 microcontroller. Once you create a new project, CubeIDE starts CubeMX, which allows you to configure the MCU with a graphic tool. By saving CubeMX configuration, CubeIDE creates the project folder structure. Modifying the configuration, customizing the project, you can also make it reference to external modules and code. But fundamentally, the project folders include everything needed, even the final executable binary to load on the MCU. So, when starting a new project, here are the first decisions we make. Which workspace to use? If creating a new one, its path name, where to store it on your PC, and what name to give to the project. Here is a quick but an important warning. CubeIDE gives you a full freedom when naming projects and folder, well, within the OS rules. But once you start adding libraries or middleware, they can generate deep folder structures. If your path is too long, you could hit a path length limit, getting issues and errors, even if your OS supports longer paths. Similarly, you may encounter errors and crashes while developing with libraries and add-ons if a project name or its path name contains spaces. For instance, TouchGFX used to throw errors if a project path had spaces. I'm not sure if that has been fixed. I always keep paths short and clean, but I've seen that time ago. So keep path names short and avoid spaces, even if CubeIDE and the OS allow it. Okay, let's go back organizing workspaces and projects. CubeIDE handles one workspace at a time. You can switch between the workspaces, but only one is open at any time. And you can only access to the projects inside the open workspace. You can open multiple projects inside that. Browse files. Even copy code between them, but again, only within the open workspace. We can also note that within a workspace, projects are absolutely independent. They can refer to different microcontrollers with different configuration. There is no any relationship between them. How we can effectively use this structure developing our projects? This is how I organize my projects into the CubeIDE system. I usually create one workspace for the overall project, and inside that I create multiple CubeIDE projects for each phase, each version, each test of it. I will have CubeIDE projects performing tests on each hardware layer, and projects for at least the last stages of the software development. This way, if something breaks, I can go back and retest the earlier version of a project. Or I can run simpler configuration testing each hardware module, allowing me, hopefully, to identify the problem to fix. Let's walk through an example. I will start here creating a workspace to store into it my new STM32 project. I'll create here, for our example, a simple TouchGFX project, like the ones we have already built on this channel. The hardware setup is a React Studio F411 board, an ILI 9341 display, and the W25 Q64 flash already on board, connected via SPI1 to the STM32. Here you see the hardware on the breadboard. I've already wired things up. This is a step-down converter powering the board from a USB-C port. I made an episode on this YouTube channel about the project and making of this device. Let's build the first project. In the very first project, I just set up the basic microcontroller configuration. I create a program just to test if it is alive and working. So, select File, New, STM32 project, and pick the microcontroller you are using, and a 411 here. Name the project. This is the first one for the microcontroller test. OK. Here I set up the clock. Blackpill has a quartz and I will use it. Enable the serial wire debug. Set up a GPIO output handling a LED. The WIAC board has a user LED connected to PC13. It is active low. OK, I'll use this LED. If you are creating your own board, well, you should really add at least a LED to it, useful for error indicators and basic debugging. Anyway, configuring the pin driving the LED, it is PC13, GPIO output, initially high, so the LED is initially off. That's all. The clock, debug, the LED. Save the project. Now, in the main loop, I will just make the LED blinking. What's the pin name? Remember that all the names assigned in CubeMX are defined in main.h. Board LED, OK. So here I toggle the LED. Add the delay. OK, the test is ready. Compile it. Flash. And run. It works. MCU is powered and alive. This is the startup test. I set it in every project. OK, next step. Now I create a project with the details of the hardware. Here is the CubeMX setup. I already defined the configuration. In this project, I'm using two SPI interfaces. SPI1 assigned to the W25Q64 flash memory already on the WIAC board. SPI2 assigned to the display and touch sensor. I'm not showing here the details about the port setting and so on. It is already analyzed in other videos and out of the topic here. At this level, I'm not enabling TouchGFX or any other optional package. TouchGFX relies on the display, so I keep the items separated. A first test, verifying the display is working. In the next project, I will test TouchGFX. So, once all the ports and pins are set, save the CubeMX project. Now, I add the libraries handling hardware. In this project, the display library and the external flash memory one. Libraries often include optional modules providing testing function. If available, install them also. Testing the touch sensor implies having a graphic display working. Here I test the display, the touch sensor after I know the display is working. Now I set up a quick test, verifying that the hardware is connected and working. Above the flash test, here I will turn on the LED if initialization returns that the memory is not available. Again, the pin name is board LED. Then, having the flash chip available, I will perform a single read-write test. I keep the flash test outside the main loop, avoiding accidentally endless writes. So here I erase the flash, I just erase the first sector, then I define two arrays. Write the flash, read it and compare the two arrays. Setting a flag showing the result. Now in the main loop, if the flash test failed, I just let the board LED blinking. Otherwise, I run the display test, available in the display library. So, running the program. A LED fixed on means a flash not found. A blinking LED means a flash not working. A LED off means flash OK. LCD display running the test means that both flash and display are correctly working. Save everything. Compile the program. Load it and run. Everything seems good. Now that I know that the display is working, I can proceed testing the touch sensor. I create a new project, starting from the configuration of a previous test. To do that, I select New from an existing STM32CubeMX configuration file. I select as a source file the IOC of the project Step 1. And I assign the new project name. Yes, Remember, no spaces to the project names. The test module has a function I will use just to see that Touch is working. Again, compile, load, and run. All hardware is working. Now we can move on testing TouchGFX. I create one more project, again starting from the previous IOC file. Now I will enable TouchGFX. I'm applying the configuration already described in the other videos about this graphic tool. OK, I created the project and added the libraries. Again, details about a TouchGFX project are out of the topic of this episode. About that, there is a specific playlist on this channel. Now I double-click the TouchGFX configuration file, opening TouchGFX Designer. And here I select, for instance, the button test example. It is a good example made by ST to test the basic features of TouchGFX. Few changes, to adapt it to the system and the display we are using. OK, TouchGFX project has been saved and configured for this device. Run the project. It works. Now we can say that the basic hardware, the software libraries and packages are fully configured and working. So we can finally start developing the real project we are working on. We will build it from the TouchGFX test project, using that configuration, that IOC file, as a starting point for our development. So, from now on, the project is really related to what you are developing, while all we have done until now is independent by the project details. Any TouchGFX project will have these testing programs made before starting to develop software. Yes, maybe you will use a different port configuration or a different display. Maybe using an advanced MCU, you don't need the external flash. But all these projects have to be available to test the various hardware and software layers we need to verify in case of errors, or more broadly, in case of unwanted results in the project under development. Next, once I start to develop software, when I reach a stable intermediate level, affordably passing a test sequence, I save it in a separate project, keeping it as a new reference for the next development. Here I will store also the release I'll publish, having registered in one workspace the whole history of my project. This way, I have here also a ready sequence of tests to follow to detect the origin of a new problem in case of it. There is a basic test showing if the basic system, the MCU, is available and working. The next project performs tests on the other hardware components. Hardware testing projects can be more than one if hardware is on layers built on top of each other. This is a good example. We cannot use a touch sensor if the underlying display is not correctly working. And for this reason, the test is on two distinct projects, the graphic display test and the next touch sensor test. And once the hardware is verified, we start testing the software packages. Again, proceeding layer by layer. Software packages assume that the underlying hardware is working. So, in the end, if the hardware is okay and libraries and software packages are fine, then the problem is me. There clearly should be a bug in the last changes I did. That's the area where I must search for the solution. Let's take a look now at some tools that STM32CubeIDE explicitly provides in analyzing code, comparing different versions of a module, identifying changes, and possibly a bug. Okay, you have many projects in your workspace, testing hardware, libraries, packages, and the last versions of your system. A usual need while developing is to compare two files identifying changes. CubeIDE provides a specific tool to do that, allowing to compare files even between two different CubeIDE projects and showing the difference. Let's try to use it. Here I have two projects testing hardware. Both have a display driver routines. Files are the same. Now I go changing something inside this one. I delete some rows. Here also I delete empty rows. Now I add some code. And change a line. That's all, I save changes. Now I select this file and the same file, unchanged, in a different project. Click on the first one and Control-click on the other one. Now right-click on them and select Compare with and Each other. CubeIDE opens a window showing the compare analysis. These lines are in the first file and removed in the second file. These lines also. These lines added in the second file. And this line was changed. Even if the version archive and handling of a software project would need specific tools like Git, CubeIDE provides a simple change history handling and allows a simple analysis in each project file. To see the history of changes, select the file to analyze. Right-click on it. Select Theme, Show Local History. Here are the dates of the last changes. And here you can open the previous version. You can even compare it with the current file version, using the tool we have seen right now. Changes history behavior can be modified via the configuration parameters available in Windows, Preferences, General, Workspace, Local History. Cyclomatic Complexity tool helps you in identifying the function you wrote needing to be redesigned and reorganized in a simpler code structure. Complexity is defined as a number of independent paths we can identify in a function. Information about the theory behind this concept is easily available here on the internet, for instance on Wikipedia, and I will add a link to it in the video description. But we can simply say that the cyclomatic complexity analysis is a way to give a score of each function in your project, indicating its complexity level. Generally speaking, a higher cyclomatic complexity is statistically associated with an increased risk of defects, as well as a greater difficulty in debugging and maintenance. So, this is not a tool helping in analyzing software, identifying changes, and hopefully bugs. This tool must be used earlier, while developing, helping to keep a simpler software organization. When I have a function with a high score, I split it in many nested functions, each one easier to understand, to develop, to test and maintain. Cyclomatic complexity analysis has its own view on CubeIDE. And if not already available in your perspective, you can open it as all the other views in Window Show View. Then click the Refresh button, because usually the view update is on request. Here, as you see, each function has its own complexity score. You can choose to see the whole set of functions available in your project or hiding the unused functions. Here you can see that some function has a very high complexity, up to 61, but it is HAL. Usually, level 10 is the higher suggested level developing software, and here also you see that level up to 10 are green flagged. Higher level are red. You can set your own acceptable level, selecting it in Windows, Preferences, STM32Cube, Build Views Setting, Complexity Ceiling. If you are a fearless developer, you can raise it, but it is not suggested. So, what's the takeaway at the end of this video? I still make mistakes when developing projects and writing software, and I probably always will. But with the right tools and a structured approach, it becomes much easier to prevent issues, spot bugs, and fix them quickly when they do occur. I hope the same will be true for you. If you found this useful, feel free to leave a comment or share your experience below. See you in the next video. Ciao!